I am Dr. Narsinga, Professor of Physics, Dean Research and Development, Marri Reddy Institute of Technology and Management. Today, I am going to explain about Schrodinger wave equation application, that is a particle in one-dimensional box. So, how the behavior of the particle inside the infinite wall potential box, that box length will be very small box. Okay, so then the electron is moving in one dimensional potential box, that is we call it as a deep potential well. It's like a well, that means it's outside very strong boundaries are there. Okay, that is high potential barriers, that is boundaries in nothing but high potential barriers. So then electron can propagate along the x-axis like this direction. So along the x-axis, the electron will be moving from one place to another place. That means if you go in a forward direction, then it will be collide with the boundary, then it will be back in same path. So that's why we will keep in the same path, the electron will be moving. So then the box length around x is equal to 0, that is the starting point, then the length will be x is equal to L. That is a L length box we are using. The electron will be moving inside the box, that is along the x-axis. Okay, so then it can propagate both in positive and negative direction. What I told, it will go and collide with the boundary, then it will be back to same path, then once again it will be collide, then back, like that. Yeah, up means forward and backward directions. Okay, so then we have to make some assumptions, that is potential energy inside the box. That means inside the box it will be along the x-axis, it won't go along the y-axis or z-axis. That's why the potential energy inside the box, it becomes 0. Here the potential energy becomes 0. So that means inside the box potential energy is 0, whereas outside the box we don't know where the particle will be. So that's why the potential energy, we say it will be infinity. The potential at above the box, that means outside the box, okay, outside the boundary, so it will be infinity potential. So that means that V is equal to 0 for 0 is less than x is less than L. So in between the potential energy is 0. Outside the box it will be infinity. So then we will assume that the particle has a 0 probability being at the walls. That means here it will be infinite potential. Infinite potential means we cannot recognize. That means there will be no possibility to stay in at a boundary place. So that's the case of 0 probability. Okay, so then psi is equal to 0, where that means around boundary. So then we cannot recognize the particle. So that means there will be no probability staying at the particle at that point. So that's why the wave equation becomes 0. Okay, then x is less than 0 and x is less than L. So like that, in between the potential energy is 0. Similarly, psi is also 0. So whereas V is equal to 0 inside the well and V is equal to infinity outside the well. So that is the box of one-dimensional box. One-dimensional is nothing but it should be in a nanometer size. Okay, but for clarity we are drawing in a big size. So the time independent, so that's a particle inside the box. Then the Schrodinger wave equation came into picture to how it will be the wave equation. So the time independent Schrodinger wave equation, in earlier class we studied that one. So that is moving in a one direction, that is along the x-axis only. So then the equation becomes dou square psi by dou x square plus 2m by h bar square into E minus V into psi is equal to 0. This is the one-dimensional time independent wave equation. Okay, using this equation, it represents is a second order wave equation. Okay, so it's a second order wave equation. Here we are considering inside the box. Inside the box means the potential energy becomes 0. So then the equation, it should be dou square psi by dou x square. That means 2m by h square, it will be in another side. So that means h bar square by 2m into dou square psi by dou x square is equal to E minus V. V is the 0, so then E is equal to psi. So this is the equation when inside the box, that is a potential energy becomes 0 inside. So that's why the potential energy in V term, it will becomes 0. So this is the one-dimensional motion of wave equation, that is h bar square by 2m dou square psi by dou x square is equal to E psi. That is a minus term, it will be like that. Or you can just write here also, that's no problem. Okay. So then minus h square dou square psi by 2m into dou x square is equal to E psi. This is the equation. So this equation is second order differential equation. So this second order differential equation, it has a definite solution also. So that definite solution is like psi is equal to a sin kx plus b cos kx. This is the equation. So where the Schrodinger wave equation, the solution of that wave equation. Okay. So here the psi is the wave function, a and b and k, these three is the constant parameters. Okay. So these parameters we have to calculate using the boundary conditions. So now boundary condition, what are the boundary conditions we have? The boundary conditions means the probability of finding the particle, probability finding the particle or electron at x is equal to 0. X is equal to 0, that is a one boundary condition. Another boundary condition is x is equal to L, because it will be inside. Since psi x is equal to 0 at x is equal to 0, that means at boundary conditions, that's a particle where it will be, we don't know. So that's why the wave function becomes 0. Similarly, x is also 0. Then the equation, that's first what the general solution, it will be psi x a sin kx plus b cos kx. Keep in x value is 0 as well as psi is also 0. So 0 is equal to a sin k0 plus b cos k0. So that means it's the b term will be 0 in this boundary condition, first boundary condition, that is x is equal to 0, psi is equal to 0. So this is a one boundary condition we got using their boundary conditions from the general solution of differential equation of second order. Then next one, that is secondary boundary condition, that is second boundary condition is x is equal to L. So at x is equal to L also, that wave function is 0, because we don't know exactly where the particle will be. That is a very infinite potential box, and its potential energy will be infinity at boundary also. Okay. Then you substitute the 0, psi 0, then x is equal to L, you substitute x is equal to L, it becomes 0 is equal to a sin kl plus b cos kl. So already b term will be 0 in our first boundary condition. Substitute that boundary condition b0, then it will becomes cos kx. Okay. Then sin kl will be 0. The sin kl will be a sin kl will be 0. So in this equation we have a two parameters. It may be a is equal to 0 or kl may be 0. So there is a possibility of this equation 0 means it may be a must be 0 or sin kl must be 0. So only one it should be 0. So then if a is equal to 0 means there will be both a and b 0 means we cannot say anything about the wave function. So that means a is not possible becomes 0. That means a is not equal to 0. That is a one observation we required, one suggestion we required. Okay. So then a is not 0, then it becomes sin kl may be 0, because sin kl is equal to 0 is a possibility. Okay. So that sin kl is equal to 0, when it will be sin kl is equal to 0, when sin kl is equal to n pi, because sine of n pi, n into 1, n is an integer, is equal to 1 2 3. Okay, n is equal to 1 2 3. So that is the integer parts. Then if it is a 180 or 360, so then sine 180, sine 360, all are, it becomes 0. Okay. So that we get kl is equal to n pi, then only sin kl is equal to 0. Okay. So k is equal to n pi by l, just a simplification of that equation. So we know the Schrodinger wave equation. Schrodinger wave equation, the wave equation we double differentiation, that equation becomes like this. So this k square term is equal to 8 pi square m into e minus v by h bar square psi is equal to 0. So this is the one term we have a Schrodinger wave equation, one dimensional. So this is related to k square value. So if you want k value, here is the k is equal to n pi by value, n pi by l. So this value we have to substitute here. Then this value becomes 1 by 2, that is a square root of this total because it's a k square value. 8 pi square m e by h square whole to the power of 1 by 2 into L is equal to n pi. Okay, where n is equal to 1, 2, 3. So here we have to square in both sides. So that means this 8 pi square m into e by h square is equal to h square into L square is equal to n square pi square. So this two sides it will be square. So then solving this equation, so we will get the energy value. That energy is equal to n square h square by 8m L square. So this is the particle in one dimensional box. So the energy, allowed energy is this one, n square h square by 8m L square. So this important equation. Here one more thing we have to our observation. So n value, n may not be 0 because n is a integer values. So that means the energy in a one dimensional box, that is electron, is energy may not be 0. That means it may not be in a rest position. So it is not rest position means it will be always moving with a nucleus. Okay, so that's also one of the advantages of quantum mechanics. Okay, the quantum mechanics tells it energy may not be quantized. That's it's not a rest. Okay, so this always it will be moving. So what is the n value? So in this equation, if you are keeping n is equal to 1, so that is call it as a 0 point energy. 0 point energy means that is the minimum energy what in one dimensional box the particle will show. That is at n is equal to 1, the value becomes E is equal to h square by 8m L square. So h is the Planck's constant, m is the mass of electron, L is the box length. So here we will calculate the energy levels. That is a 0 point energy, that is becomes E is equal to 1. If the energy is first order, that means higher energy levels, that is first level or second level, third level, if you want to calculate, then you just make it n is equal to 1, 2, 3 like that. Okay, so then the 0 point energy is n is equal to 1. It's not a 0 actually. So that is a possible energy. So it will be it always have some kinetic energy because it's not in a rest position, because this much energy is there, h square by, if n is equal to 1, it becomes h square by 8m L square. This much energy is still there. Okay, so that means the electron is not in a rest position. It always have some kinetic energy. It is always moving surrounded by nucleus. Okay, so this is also one of the it will be consistent. That means it will also tells the Heisenberg uncertainty principle, because we cannot make two parameters at a time accurately. That's a point also it will tell. So this zero energy in both space and time place. So similarly, what is the different type of psi value? That is one wave equation, that is psi. If it is a psi, that is a sin n pi x by L. Actually, a is equal to root 2 by L. If you just sin wave function with different energy levels, how it will be? So at n is equal to 1, that is a 0 point energy. So that we can make the particle, it will be probability of the particle at center point we can get. That's a maximum probability at center. That means at center point the energy will be maximum. So okay, so then if n is equal to 2, there is a two possibilities. One is the maximum possibility at n is E is equal to at maximum value, that is n by 4th or something. X by L means it's a fourth value. So here 3 by 4th also we are getting another maximum. So that's why, so there is a second valence, that is energy level, second level energy. It will be at, we can recognize the particle at probability maximum is 2 points. Similarly, n is equal to 3, there is a 3 points, we will get the particle. So that means the box length, it will be 1 by 3rd or means half almost, then there will be 2/3. There is a different positions, you will get the particle, maximum probability getting the particle. Similarly, n is equal to 4, you have 4 maximas, 4 probability maximas. Okay, So it may be negative or positive. That's only finding the particle. It will be like that. So Bond interpretation is there is a psi into psi star, that we call it as a complex sine wave, that is psi into psi star. It becomes 2 by L into sine n pi x by L into whole square. So this equation and this equation you have to remember, and you have to write in this way. So here it is first one is psi 1, that is this equation. So the second diagram, it tells the psi square, that complex one, psi into psi star. So here also, if you are at zero potential energy, so here also the probability of finding the particle at center, that is only one probability maximum will be there in a first, that is a 0 point energy. Whereas in at first valence that means first excited energy, so you the probability of two positions. Okay, there is a maximum probability in two positions. So similarly, n is equal to 3, that is a second energy level. So then it will be three positions. So n is equal to 4, it will be, it's a third excited state, that is where we can get the particle at maximum probability is 4 points. So this is tells about how the energy is distributed in a first excited state, second excited state, third excited state, like that. So this equation for one-dimensional box energy equation is this one. So you can calculate the zero potential energy and first excited energy level, how much it will be, second excited level, third excited level. If you know the zero potential energy, you can calculate from zero potential energy E1 is to E2, it will be 1 is to 4, because n is equal to 2, 2 square is a 4. If it is a third one, it will be 9, 1 is to 4 is to 9. If you know the zero potential energy multiplied by 9, you will get the second excited state. So third excited state, that is E is equal to 4, n is equal to 4, then it becomes 16 times. So this way the energy distribution in a particle in one-dimensional box. Okay, so this one-dimensional box story. Then we will go for what is the Born interpretation. So Born interpretation of wave function, it tells that there is a psi value, that is a function is psi, the wave function. So it won't have any meaning actually. The psi means if you represent psi, it won't give any, if it is some length or width, whatever, we won't give anything about this wave nature of psi. Okay, but it will give you the means how it will behaves, that it will give. Okay, but it won't have any physical meaning. It is only mathematical tool, that is a psi is a mathematical tool. But if you multiply it by its conjugate psi into psi star, so you will get the maximum probability of the particle where it will be. Okay, so that tells where the particle is inside the potential box. If you psi and psi star, it will tell. Okay, so that is probability of finding the particle. It's only we can get the probability of finding the particle. So where it will be maximum, where it will be minimum, that depends on this one. Okay, so then if you give this psi star will give definite meaning. What I mean is we can say it will be at that point it will be maximum. So that tells this according to Born interpretation, this psi, the wave function, they represent like this. So similarly, another topic, there is a Heisenberg uncertainty principle. This is a simple suggestion, means it will be, it's the definition of this Heisenberg uncertainty is tells that is any physical quantities, the two physical quantities we cannot measure at a time accurately. At that point means at that point of time, so we cannot measure two physical parameters accurately. That means without error, we cannot measure those two parameters. So it may be momentum, or it may be position, or it may be energy or time, or it may be angular velocity or angle. So these two parameters we cannot measure accurately, because if your single wave is there, So we can measure exactly what is the position, what are the things we can measure exactly. But if the waves are bunch of waves, that is a wave path or wave bunch will be there. So here the calculating the position, it will be difficult. But here the momentum we can measure easily. So like that. So if you measure one accurately, another one maybe some error will be there. So for that purpose, they represent one equation, that is a measured quantities. If you take it as a delta P, that is error in momentum, okay, or uncertainty in momentum multiplied by uncertainty in position. Uncertainty or error, it will be same meaning. Error in momentum and multiplied by error in position. So this value, it will be less than or equal to, or sorry, greater than or equal to h by 4 pi. So that means h by 4 pi itself is very, very small value. H is in terms of 10 to the power of minus 34. So that means the error is at the very smaller level. So this error is applicable only for microscopic particles. That means if the electron is there, so that means it is in terms of very small value. This means its moment. What I mean is velocity is speed, but there is a mass of the electron. It's almost 10 to the power of minus 31. So like that, the very small particles, it will be applicable this uncertainty. If with the big particles, why it is not applicable means big particle also it will be applicable, but momentum is in kilometers. So then it will be kilometer or kilometer 0.01. There will be not much difference. So that means that error will be may not be that accurate. So that's why the uncertainty principle in every material it will be possible, but only we can recognize in microscopic particles. That's the important point in Heisenberg uncertainty principle. This is momentum, error in momentum and error in position. This is greater than or equal to h by 4 pi, or sometimes we can write h bar by 2 also. Okay, this h bar is another parameter. It is equal to h by 2 pi. So that way, some books we can write, we can see h by 4 pi or h bar by 2. So it's both are correct only. Okay. So this is momentum versus position. So similarly, there is another equation. There is a energy. Energy, uncertainty in energy is the delta E. Similarly, uncertainty in time, that is delta T. So these two parameters multiplication also greater than or equal to h by 4 pi. So that means any two physical quantities, if you measure exact value of delta E, there is error in time. If you are exactly you measure the delta T, that is a time you are accurately you measured. Okay, at the time that energy may be some error. So in that way, so the error will be h by 4 pi greater than or equal to h by 4 pi. That is energy versus time relation. Okay. Similarly, there is a angular momentum. Delta J is the angular momentum and theta is the angle. So delta J, if you are measuring accurately, there is a possibility of error in angle, that is delta T. So similarly, if you are measuring exact theta value, then there is a possibility of error in delta J. So in this way, so there is a terminology that delta J and delta T, these two are error parameters, that is uncertainties, okay, in angular momentum as well as angle. So this error also, it will be greater than or equal to h by 4 pi. So that is Heisenberg uncertainty principle. So the another small topic, that is matter waves. So what is mean by matter waves? We already studied in an earlier video. So that's whenever the particle is moving with velocity, it behaves like a de Broglie hypothesis. So that means when whatever the particle is applicable to de Broglie hypothesis, those waves we call it as a matter waves. So these matter waves, we know that lambda is equal to h by mv, that is de Broglie hypothesis wavelength. So h by mv, that is h is the Planck's constant, m is the mass of the particle, v is the velocity. If the mass of the particle is reduced, what will happen? The lambda value will increase. So that means If it increasing here, this should be decreased. Okay, so that means it related to mass, that is lambda is directly proportional to 1 by m. Similarly, if the velocity decreases, lambda value also increases. This is also relation is lambda is equal to, lambda is directly proportional to 1 by v. So that depends on the velocity as well as mass. These are the, we can say, properties or characteristics. Okay, if v is equal to 0 means that electron is in a electron or particle in a 0, means there will be no momentum. So that is not possible in according to quantum mechanics. So that's another case. Okay, it should be moving only. So whether the part here, the matter waves, it may be charged or uncharged, is possible, the wave nature. Okay, the waves are produced whether the particles are charged or uncharged, whereas in electromagnetic wave means it requires some positive charge of the particles. Okay, so the charged particles movement, we call it as a electromagnetic waves, whereas normal waves, it may not require any charge. Okay, so it's matter waves, it may not require the charge. Without charge also, the wave nature it will be produced. So that's why this kind of new matter waves are produced. Okay, so these matter waves are always, the velocity of these matter waves always greater than velocity of light. Okay, so that's another important topic, where the velocity of light means most of us, we are saying the velocity of light is very high, any other things, but these matter waves is also greater than the velocity of light. How it becomes? So we can say there is a mass energy relation, and the particle is moving. Moving means there should be some kinetic energy. So that kinetic energy is half mv square, where according to Einstein energy mass relation, we know that E is equal to mc square. To these two energies, we equalize these two energies. So we will get the v square is equal to 2 into c square. That means v is equal to root 2 into c. Root 2 means 1.414 into c, charge of the means light velocity. Okay, so that means this much times light velocity is equal to, that's matter waves velocity.